An introduction to using a special kind of discretization for advection-diffusion equations. So we've seen before how central differences are great for diffusion but not really for advection, and that's because of the directionality of advection being from one side to the other like a wind. So central differences use an equal weighting, whereas a wind is definitely directional, so you want to weight the upwind side more. And we remedied that with using an upwinding method, but that's not great in the sense that it's only first order accurate. Here's an alternative approach following Patankar to take advantage of an exact solution for advection diffusion problems to build a unique and accurate method. Later, when we talk about hyperbolic systems, we'll learn how to do other methods for treating the advection term. So here's our so consider the one-dimensional steady advection diffusion equation. So use velocity times some scalar phi that we're transporting. U d phi dx equals gamma d2 phi dx squared. And you can divide through by u if you like. If we assume a domain of length L with Dirichlet boundary conditions, so on the left we'll let phi equal phi 0, and on the right we'll let phi of L equal phi L at the end of the domain L. Then we'll also assume the Peclet number, PE, is UL over gamma. So this is the same as before, where we're going to use the Peclet number as whatever the length of interest is. And sometimes that'll be the whole domain, sometimes that'll be like delta x. So this steady advection diffusion equation has an exact solution. And the exact solution is given by this blue equation. This equation can be verified by direct substitution into the ODE. So if you solve for phi and plug it in, you can see that it satisfies the ODE. And you can see how phi is centered and scaled. So it's phi minus phi left edge divided by phi at the end of the domain minus phi at the left edge. And when I say left edge, I mean the domain goes from 0 to L, increasing towards the right. So anyway, this quantity on the left will always vary between 0 and 1 because of the way this is centered and scaled. The subtraction of the left here, phi 0, that's what I mean when I say centering it. So we subtract off the left edge and then we scale it by the maximum difference between the edges. And then this right-hand side is written in terms of these exponentials. So we could call this left-hand side in terms of this centered and scaled quantity, we can call that phi hat. And this is a really common thing to see in heat transfer, for example, where you might have a reduced temperature, sometimes called theta. So let's look at this equation a little bit. So if the Peclet number is 0, then that means that the velocity is really small compared to diffusion, and we basically just have a diffusion problem and the solution is linear. So if the Peclet number, if u is 0, then this term is 0, and we just have diffusion. And if the second derivative is 0, then it's a linear profile and with no source term. There's no source term here, so we just get between two boundary conditions, you would get a linear profile, which is consistent with having zero curvature. Okay, so that's what happens if the Peclet number is 0. If the Peclet number is very large, then it means that here's the Peclet number again, then it means that the velocity is really high compared to, for some L, if the Peclet number is large, it means that U is large compared to the diffusivity. And we would have a positively curved solution where U0 persists over most of the domain. So in other words, if you've got a boundary condition where you've got some phi value and then some lower phi value on the right, and the wind is blowing to the right, then this phi 0 is gonna persist over most of the domain. And the gradient becomes large at the left. So let's look at this with an actual plot. So here's a plot of phi hat, just plotting this blue equation. This blue equation here, calling this quantity on the left phi hat. And we're just vary the Peclet number. So we're setting this up, and I think I misspoke before. We're setting this up so that on the left phi hat is 0 and on the right phi hat is 1. And if the Peclet number is large, you get this purple curve. And that means that the velocity is blowing from left to right. And it's effectively blowing the left value at 0 across the domain. And that value persists almost to the very edge where it finally jumps up to its other Dirichlet boundary condition at 1. And it persists because velocity is so strong that it's advecting it across the domain. At some point, though, we know the equation says that diffusion balances advection. So at some point, you have to have diffusion being important. And the way that diffusion exerts its importance is by saying, I'm going to have a higher gradient. So even though the diffusivity is small, if you get a high enough curvature here, then it can balance the advection term even when u is high. And so close to the edge, you end up with this high gradient. The same thing happens if you change the sign of the velocity. So if you make the velocity, if the Peclet number is negative, then it goes from right to left, and then this right value persists over most of the domain before finally jumping down to the imposed Dirichlet condition on the left. And when the Peclet number is 0, you have this diffusion-only behavior that's happening. So it's really useful to pay attention to this case when we're talking about convection, advection, diffusion, saying what are the sort of the limits as these terms have different levels of importance. So central differencing effectively assumes that the profile is linear, like diffusion, takes advantage of that kind of behavior. Upwinding assumes the profile is constant, and that works a little bit over a portion of the domain, but not necessarily for the diffusion portion later. And both of those, of course, are reasonable approximations in the limit of diffusion or advection. But let's see how we can use the exact solution to tell us how to choose a phi profile between these points. So, so let's analyze that. We have the exact solution in this case. It's a particularly simple case, but the insights that we get from the exact solution can be used to build flux approximations, like variations on upwinding or central difference. We're going to learn a new method, not upwinding, not central difference, but something else that's going to be informed by the way that we do exact solutions. And here's how we can do that. So if this is our ODE, then we can reformulate that as d dx of u phi minus gamma d phi dx. So basically, we're going to assume that the velocity is constant, and that allows it to go inside of the derivative here. And then we combine the two terms. So we have d dx of u phi minus gamma d phi dx. And that's not, moving that velocity inside isn't really an assumption because of the continuity equation. And this quantity here in parentheses, we're going to call that a flux. So we have the advective flux and the diffusive flux. And basically this is the divergence of the flux equals 0 when there's no source term, meaning the quantity phi is conserved. So our equation looks like this. df dx is 0. And recall, with finite volume methods, we're really interested in describing those in terms of fluxes. And then when we integrate the equation over a finite volume, we end up with the flux at the east face minus the flux at the west face equals 0. So this is our new equation, and we know our flux is going to be ue phi e minus gamma e d phi dx on the east face, and similarly for the west face. So there's our flux, finite volume approximation. These are our equations that would describe the whole thing. Okay. So for a given face E, its right neighbor is big E and its left neighbor is P, big P. And we're going to take those as known boundary conditions. So even though we might have a finite volume consisting of lots of grid points, for this problem, let's just consider one volume, and we have a left neighbor, a right neighbor, big E and big P, and we'll just take those as known quantities and then apply our exact solution to this. And we'll let L equal delta X, which is the grid spacing. So we're basically solving for the exact solution. We're discretizing our ODE in a finite volume sense over a grid cell, and then we're going to apply the known exact solution for that particular problem. So let's solve our exact solution for phi and its derivative. So here's our exact solution, blue equation. If we solve that for phi and also the derivative d phi dx, then we have these quantities here. And we want phi and its derivative because the flux has phi in it and it has its derivative. So the exact solution that we already found is phi is anyway given here, and there's its derivative. And for convenience, I'm going to call this quantity phi e minus phi p over e to the p Peclet number minus 1. We'll call that gamma, just so we don't have to write it everywhere. Okay, and so this gamma is a constant in the sense that it just depends on the Peclet number and the values of phi at the neighboring points. Okay, now we can insert these for phi e and the derivative in our expression for the flux. So if we insert this in for phi e and the derivative in for the derivative here, then the flux looks like, here's our flux. Then our flux looks like phi on the east face is ue phi p plus the flux plus ue gamma, anyway, this quantity here. Do the insertion, this is our flux. Now, I didn't write it this way, but you can use, if we're using a finite volume method on a regular grid, then when we say f at the east face, we really mean x at the east face divided by delta x. And that quantity will equal 1/2 because the face is halfway between the cells if we're using practice A. So importantly, what you can see here is that the exponential terms cancel in this equation. It's just lovely when things cancel out, and here we get this really great cancellation. So first thing we recognize when we do this substitution is that gamma e Peclet number over delta x, that's just ue, because the Peclet number is ue delta x over gamma, so this whole quantity is ue. And then you have a minus gamma ue times this derivative, and here's a plus gamma ue times this derivative. So those two terms cancel, and you're just left with the flux equals ue phi p plus ue minus 1, which gives you this. Crazy. That is a really simple expression for the face flux. Remember, if we were doing upwind, the face flux would just be phi upwind, and if we were doing central difference, the face flux would be, well, the advective part of the face flux, if we were upwind, would be u upwind times phi upwind. And if we were doing central difference, you can, anyway, we've done both of those. And so here we have a different representation for the flux at the face. That's the point, based on our exact solution. So now let's put the gamma back in. Plug this gamma back in, and we have these two lovely blue equations here. So here's an alternative method based on the exact solution for computing the fluxes at our faces. Okay, and remember, here's our finite difference equation for this ODE, and here's how we evaluate those fluxes. So if we do this, we're going to get the exact solution. So why would you ever, if you know the exact solution, why would you ever go through the work of doing a finite volume method on it? Just take the exact solution. You already have it. And the reason, of course, is that we're going to apply this flux formulation to problems where we don't know the exact solution. Maybe there's a source term, maybe it's a complicated source term, or maybe it's multiple dimensions. We can still apply this kind of method for evaluating the fluxes. Of course, now it's an approximation, but it's going to be a better approximation than the way that we deal with fluxes using interpolation and upwinding and central differences, which we've studied so far. So if you plug these into this ODE here, FE minus F west, if you plug these in and then collect terms, then we have the coefficient of phi west and the coefficient of phi p and the coefficient of phi east, like usual. And then this is an AX equals B system that we can solve for the various phis. Okay, and this would be a linear problem if the velocity is known. Of course, this PDE, this ODE here is linear. If the velocity is known, then you can just solve that directly with the linear solver. And again, so complicated source term, or maybe it's unsteady, or maybe it's multidimensional. That's what we're going to use these flux formulations in. The same flux formulation we can use in more complicated situations. So this is pretty cool and very clever, kind of a creative method for using what we know about exact solutions to find flux formulations for more generic situations where we might not have an exact solution. The problem with this is that exponentials are really expensive to calculate. So doing a lot of exponential calculations increases your cost a lot. Here's a link to an article that describes the cost of doing different operations. So for example, it's really cheap. Addition, subtraction, comparison cost 1. Multiplication costs 4, so it's about 4 times more expensive to do multiplication than addition, subtraction. The next level, division and modulus. Division is expensive. Division is more than twice as expensive as multiplication, so it gets a weight of 10. So don't divide by 2, multiply by 0.5. It's cheaper. The red are the really expensive things. Calculating an exponential or trig functions or doing a power, like, I don't know, 10 to the 1.83, that's really expensive. And the exponential costs 50, so roughly 50 times more expensive to calculate an exponential than to calculate an addition operation. And so you want to be careful about using exponentials. So in Patankar's book, they approximate these exponentials with polynomial approximations. So you can see all of these terms, exponentials, are always appearing as u over e to the Peckley number minus 1. And I'll just note, because of our grid, we might have a non-uniform spacing, etc. So we're extending the notation here. We're calling PE the Peckley number on the east face, and PW can be the Peckley number on the west face, where you might have different delta x's for each one. So a variable grid size is built in to this, these blue equations here. So the exponential terms, they look like u over e to the Peckley number minus 1. And we can rewrite u in terms of the Peckley number. So u equals Peckley number times gamma over delta x. And we'll call this last part, and we do this because we want the whole term to be written in terms of the Peckley number, the exponential part. On the left, it's got u in it and p, and so it's easier to deal with if it just has p. So now this quantity right here is just a function of Peckley number alone. So we'll call this quantity t, and then we'll write t equals p over e to the p minus 1. And so this is, if you want to get rid of the exponentials, then you want to model this term right here. And Patankar does that in 3 parts. He gives a non-exponential curve fit that he calls the hybrid scheme. So he says, if p is less than minus 2, then this quantity t can be taken as minus p. And if Peckley number is between minus 2 and 2, then you can replace this quantity with 1 minus p over 2. And if Peckley number is greater than 2, you can assume this whole quantity is 0. So he also gives a smooth polynomial fit. So this is kind of like 3 piecewise functions. They're piecewise linear functions to replace this exponential term with. He also gives a smoother polynomial fit that I'm not showing here. But here's what this looks like. Here's this term t that we want to replace as a function of the Peckley number. And you can see that his fit does actually quite well. So you shouldn't have any qualms about using this red curve, this fit, in place of this exponential term. And so you can use this directly. So wherever you see these terms here, you can recast them in terms of the Peckley number like this. Each of those terms can be recast like that. And then you can call this term t, and then you can evaluate what that thing should be. T equals minus p if your p is less than 2, and t is 1 minus p over 2 if you're in this range. T is 0 if you're greater than that. And so that works really great and is pretty easy to apply to these finite volume methods. And that's a brief and rather succinct discussion of how you can use these exact solutions to inform and create more accurate or more accurate representations of the flux for problems that include both advection and diffusion, which is quite common in conservation laws. Thanks.